Chapter 5, Conversions within Measurement Systems. At the end of this chapter, we should be able to identify, convert, and calculate within household system measurements of weight and volume using both the ratio and proportion method. Identify, convert, and calculate within metric system measurements of weight and volume using both the ratio and proportion method and dimensional analysis. Notice I didn't mention that before because I won't be showing any examples using dimensional analysis, but book does have examples of it. Identify, convert, and calculate within apothecary system measurements of weight and volume. So we will cover these keywords throughout the chapter. This chapter focuses on converting from one unit to another within the household metric and apothecary systems. All conversions and most pharmaceutical calculations can be completed using one of two basic calculation methods, dimensional analysis or ratio and proportion. So you can get the answer from either way. I learned ratio and proportion, and I think it's much simpler. But the newer way that some students learn how to do these in school is dimensional analysis. So whatever works for you works best. The book does give examples of both. Um, but I will just do examples using ratio and proportion. So if you want to look at those examples, they are in the book. So the US household or customary system. So how many inches are in 2 feet? That is a fairly simple equation from people in the United States because it is used in everyday life. We know that 1 foot equals 12 inches, so 2 foot will obviously equal 24 inches. That is an example of the ratio and proportion method of solving a conversion. The ratio and proportion method is solved by cross multiplying and dividing. Identify the unknown unit of measurement, find the known equivalent, write the known equivalent in a fraction on the left side of the equation, write the unknown desired equivalent in a fraction on the right side of the equation using x for the unknown value, cross multiply the numerators and denominators, divide to solve for the value of x. All right, let's do example 5.1.
All right, example 5.1. How many inches are in 2 feet? We know that there are 12 inches in 1 foot. So that's our conversion factor. So on our proportion, we know we need to have the same units directly across on the other side. So we have 2 feet, 2 foot. How many inches is that? So then we're going to cross multiply diagonally. So this becomes 1x, which is really just the same as x. And then 12 times 2. So I'm just simplifying my problem down here. 12 times 2 is 24. So x equals 24. We don't have to do anything else because x is already alone. So our answer is 24 inches. How many tablespoons are equivalent to 7 teaspoons? Once you know all of the basic equivalencies from chapter 4, this becomes much easier. So we'll have a little sheet for you too as well. We can see from table 4.3 that 3 teaspoons is equal to 1 tablespoon, therefore. So that's our conversion factor. 3 teaspoons is equal to 1 tablespoon. And we could write this however we wanted. If we wanted to put tablespoon on top and teaspoon on the bottom, that wouldn't matter. We just have to make sure our units are the exact same directly across. And we want to know how many tablespoons. So X tablespoons are equivalent to 7 teaspoons. So we would do 3x is equal to 7 times 1, which we already know is 7. I'm going to just rewrite it as 3x equals 7. Now we want to get x alone, so we got to get rid of that 3. To do so, we're going to divide by 3, which gives us x on this side. And then we also have to do the same thing over here. So 7 divided by 3 is 2.33. However, we're working with a household system, so we actually can't make that a decimal. We need to leave it as a fraction, but we cannot leave it this way. So what we need to do first is do 3 into 7. So how many times does it go in there evenly? Well, 3 times 2 is 6, and 3 times 3 is 9, so it's going to be 2. So 3 times 2 is 6. We have 1 left. So that becomes our numerator, and our denominator becomes the 3 over there. So our answer is 2 and 1/3.
Dimensional analysis is another method for converting between units. Some students prefer using this method since it's easier for them to keep track of units. For this reason, the book does cover DA exclusively when dealing with multi-step calculations. A conversion factor is a ratio that is equal to 1 and is used to change one unit to another. Because it is an equivalent to 1, it does not change the value of the answer, only the unit. While inches equals 1 foot is a conversion factor, 12 inches divided by 1 foot has a value of 1 because they are equivalent amounts. And in dimensional analysis, you identify the unit of the answer needed and follow it with an equal sign. Set up a fraction such that the unit of the desired answer is in the numerator of the first fraction of the DA equation. This unit will never be canceled. Set up the next fraction in the equation so the unit of its numerator is the same as the unit of the denominator of the first fraction, so they will cancel when the fractions are multiplied. Continue this pattern when dealing with multi-step conversions. So we already did examples 5.1 and 5.2, which are the same as examples 5.3 and 5.4. This is just using dimensional analysis, and you can see the breakdown right in the middle here where they work it out.
Example 5.5, 24 tablespoon is equivalent to how many cups? So this is in the book, they're showing using dimensional analysis, but we are going to just use proportions. So we need to find a proportion between tablespoons to cups, but there isn't one. I mean, there is technically, but we don't have one on our sheet and there's not one in that table. So we have to do 2 different ones. First, we're going to use the 2 tablespoon equals 1 ounce. We're going to convert it to ounces, and then we're going to convert the ounces to cups. So we said 2 tablespoons is equal to 1 ounce. And we have 24 tablespoons. So how many ounces is that? And we'll do 2x equals 24 times 1, which is just 24. So we have 2x equals 24. We want to get rid of the 2. So x is alone on this side. That's what we're solving for. And then we also have to do the same thing to the other side. So 24 divided by 2 is 12. So it's 12 ounces. So now we want to use our conversion factor between ounces and cups. So 8 ounces equals 1 cup. And we have 12 ounces. How many cups? So we could do, so 12 divided by 8 is 1.5. So we can do the long division and do 8 into 12, but hopefully you guys know that 1.5 or 1.5 is just 1.5.
Because a metric system is based on units of 10, conversions can be made within the system by moving decimal places. This is a quick method, but a thorough understanding of the relationship between units is needed to master it. So DA and RMP can be used as well, which I prefer. Yeah, you do it that way. So this is just a little chart of the metric measurements of mass used in pharmacy and just kind of explains that there is the table 5.2, which shows metric conversions used in pharmacy for weight and volume. Also keep in mind that this information is on that conversion sheet, which is in your weekly study materials. I think it says highlighted conversion sheet. The units used for weight in pharmacy are from largest to smallest, kilogram, gram, milligram, and microgram, with 1,000-fold or 3 decimal place difference between each closest measurement. The units used for volume in pharmacy are from largest to smallest, liter and milliliter, with 1,000-fold or 3 decimal place difference between each. The main conversion factor that is used in pharmacy for volume is 1 liter equals 1,000 ml. And that is going to be something that you just are going to want to make a really comfortable spot in your brain for, because it's something that if you work in pharmacy, you're going to need to know, especially if you are working in compounding or hospital pharmacy. The placement of the decimal place is based on moving through powers of 10 by moving the decimal point. First, determine the number of the decimal place difference between the two numbers. When converting from a larger metric unit to a smaller one, move the decimal point to the right by the number of the decimal place difference between the two, or multiply by 1 plus the number of zeros in the equivalent, which is the large unit to smaller unit, then multiply. This method can be verified or checked by using a ratio and proportion, or DA as well. The following examples depict moving the decimal point, multiplying by 1 plus the number of zeros difference, ratio and proportion, and DA. All right, so let's do example 5.6.
Now, so we have 1 liter is equal to 1,000 milliliters. And we have 1.2 liters. How many milliliters is that? So we have 1x, which is just x, is equal to 1.2 times 1,000. So we'll get out our calculator and just do 1.2 times 1,000. So that is going to be 1,200. So if 1 is 1,000, then it makes sense that 1.2 is 1,200. All right, so example 5.7 is the same, trying to move it from the decimal points, but we're just going to do proportions. So we have 5.4 kilograms and we need to change that to milligrams. So looking at our conversion sheet, we don't have a direct conversion between kilograms to milligrams. So first we're going to have to convert it to grams and then convert grams to milligrams. So we'll have to do two proportions, which I still think is easier than matching everything up for dimensional analysis. So 1 kilogram is equal to 1,000 grams. And then we're going to use 1 gram equals 1,000 milligrams. So 1 kilogram equals 1,000 grams. And we have 5.4 kilograms. How many grams is that? So this 1x becomes just x is equal to 1,000 times 5.4. So 1,000 times 5.4 equals 5,400 grams. Now we have to convert those 5,400 grams to milligrams. So we'll just place our grams up here. How many milligrams is that? So this again will become 1x, which is just x, equals 5,400 times 1,000. So x is equal to 5,400 times 1,000, which is 5,400,000.
Converting from a smaller metric number to a larger metric number, first determine the number of the decimal place difference between the two numbers. When converting from a smaller metric unit to a larger one, move the decimal point to the left by the numbers of the decimal place difference between the two, or divide by 1 plus the number of zeros and the equivalent. So the small unit to large unit and then divide. And then let's go ahead and do example 5.8.
Example 5.8. So we're moving from milligrams to grams. So we should already by now know that 1 gram equals 1,000 milligrams. We'll place our 5 milligrams down here. How many grams? So we have 1,000x is equal to 1 times 5, which is 5. And then we'll divide the side by 1,000 to get rid of that. We also have to do it to this side. So 5 divided by 1,000 is going to be 0.005. Remember, we always have to have that leading zero before the decimal. So example 5.9, we already used this conversion factor of 1 kilogram is equal to 1,000 grams. And we want to go from grams to kilograms, so I'm gonna use this for one side of the proportion. And we have 500 grams. How many kilograms is that? So we have 1,000x is equal to 1 times 500, which is just 500. And we want to get x alone, so we got to get rid of that 1,000. We now have x alone on this side, but we have to divide that side by 1,000 as well. So 500 divided by 1,000 is going to give us 0.5 kilograms.
Apothecary system of measurement. The measurement of grains is still found on labels of nitroglycerin, codeine, phenobarbital, armour thyroid, aspirin, and ferrous sulfate. Some physicians will order these medications as well as acetaminophen in grains, which is the apothecary unit used most in pharmacy. Apothecary symbols are found on the ISMP list of error-prone abbreviation symbols and dose designations. They will be used in chapters 5 and 6 only. Apothecary equivalents that will be used as conversion factors in practice problem C are found in table 5.3. And this is also going to be on that sheet that I have for you. But you can see them here. And let's do our first problem, example 5.10.
All right, so if we look at our conversion sheet, we can see that 1 fluid ounce is equal to 1 fluid dram. So I'm going to put 1 ounce equals 1 1 fluid ounce equals 8 grams. So I'll put that on one side of a proportion. And we have 2 ounces. How many grams is that? So this 1 times x just becomes x. So 1x is just x. And then 8 times 2. So x is equal to 8 times 2 is 16. So that's 16 fluid grams. And we would need to do FL, so our symbol. And then we would need to do 16 in Roman numerals. Which let's Google it. See how bad I am at Roman numerals. So XVI. This would be our answer.
Three measurement systems are used in medicine. The household system used most commonly on a daily basis in the United States is sometimes used for administration of liquid medications at home if an appropriate dispenser is not provided. Using the household system for volume provides only approximate measurements because of the differences in flatware and measuring spoons. It may lead to an inaccurate dose when used for administering medication. So that's why we always want to give the patient a measuring device for liquid medication when it's prescribed. The metric system is used as a standard unit of measure throughout the world. Most medications are labeled and dosed in the metric system. The final system, rarely used today but is still found with some medications, is the apothecary system. Although this system is not popular and its use is being discouraged, these measurements are still seen occasionally with some directions. And you will see mention of it on the PTCB. Ratio and proportion in DA may be used for the calculation of conversions within a system. With the metric system, a decimal may be moved as a shortcut to make the necessary conversion.